So we're going to do mediation here in just a moment. Before we do that, I just wanted to go through something really quick here. When it comes to plotting these things, I just want to make sure that everybody understands what we're talking, what all of this stuff is doing. When we're talking about, this is not going to be in the video, unfortunately, but when we're talking about a regression equation, right, and we want the mean of something, we have y equals, b1 times x plus b2 times m plus b3 times x m plus r or I or whatever you want to call that, right? And this equation, if you're just trying to get this slope, right, it's going to vary as a function of this. And we're basically fixing these other two slopes. So if you took my regression class before, you'll know that's why when we have this stuff here, each one of these is just the values of the slope of b1 here, our x coefficient, right? Because the other slopes never change. Remember, I showed you that when I reran it. I was like, look, we put in high levels, we put in low levels, they never change. And it's because you're really just saying like, okay, I'm going to call this 0, and then now I'm going to call it minus 0.88, now I'm going to call it plus 0.88. And it's always multiplying this times that exact value, right? So it never really changes. Same here, if this is 0 versus whatever, it's never going to change. This is never going to change. But this will change based on what you've got right here for x. And so, knowing that, you could go in and create a 4-way interaction, a 5-way interaction, which is nonsense, by the way. But certainly 3-way interactions are not nonsense, and you see those all the time. And if you wanted to create a 3-way interaction, you would have something that looks like, somebody walk me through this. What's our equation going to look like for a 3-way interaction? We're going to have y equals, oh, I missed something here, didn't I? I have r. Should be plus I plus r. So I'm sorry. Equals what? What's the first thing that I need here? For a 3-way interaction. b1 x plus b2 m1, good, plus m1 m2 plus what, Jake? b5 x m1 plus b6 x m2 b7 x x m1 m2 plus I, and then plus r, which doesn't actually get calculated in here. What is r? Yeah, it's just our residual, right? And you can remove r if you put a hat on y, right? So anyway, in this equation, this is fixed, 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 right? All of those wind up being fixed, and the only thing that would move at all is that slope right there. Make sense? Yeah. And of course, I moves, right? All right, cool. So let's move on now, and let's start looking at mediation. I'm going to minimize this for right now. I'm going to close this because we don't need it at all. Don't save. The next thing that we want to do, I'm going to remove our interaction for right now from our equation. We have, I'm going to be honest, I don't remember exactly. I think drink was the variable that I was using here. So let's grab drink. Let's just throw drink in here. Oh, thank you. Somebody's on top of things. Drink goes at the front. If you don't have it at the front, it will not work out. Drink on NaCDTS CALS. And we save that. And we hit run. And this is, again, going to be a fully saturated model, I'm pretty sure. Scroll down here and have a look. Yep, we still don't have fit indices. And something odd is going on here because I thought that one of these predict, oh, it's not drink. That's what it is. It is alcohol problems, controlling for drink. Where's my alcohol problems? It's not AP control. I thought it was AP tote, but I don't. There it is, AP tote. This is total alcohol problems. Let's keep drink in there just as a covariate, and let's add in AP tote, and then let's go like such. AP tote on all of that stuff. So now we're looking at alcohol problems, controlling for the amount of drinking that a person engages in. We scroll down. We should get fit indices this time, actually. We have a single degree of freedom, a chi-square that is pretty close to 0. What does that tell us? Model's got pretty good fit, right? Of course, 1 degree of freedom. It's hard to really judge that. RMSEA is very, very low. CFI is very low. TLI, of course, you can have a TLI that goes above 1, and that's because it is penalizing you for the number of parameters, or trying to at least. SRMR looks fantastic. All of this stuff looks really, really good. And we can see that all of the things are statistically significant. Is this what everybody else has so far? Yeah. Then we have our R squared down here. We have an R squared for negative affect and an R squared for alcohol problems. AP tote is alcohol problems. We have no modification indices. So far, that's looking pretty good. What is our indirect effect? Anybody? So M plus, we can go and we can calculate new parameters using M plus. We're not going to do that today. We are going to do that when we have our class on structural equation modeling and path analysis. Today I'm going to show you the easy way. Let's go back to our thing, our model here. We're going to type model indirect. I always mess these up. Let me see if I get it right today. NaINDCDTS, NaINDCALS. And this is the indirect association between negative affect and DTS, and between CLs and DTS. I think I did that right. Let's have a look and see. I might not have. There's our model fit and everything that goes with it. Standardize, R squared. Yep, I did do it right. Here is our indirect effect. We have a total effect of this. Oh, aha! So I did to NA. Actually, if we look at that again, let's see who can troubleshoot this for us. I screwed something up here. So our total effect is 0.243, and our total indirect effect is 0 with standard error of 0 and estimate here. What's wrong with these two things? They're both wrong, right? What did I do wrong here? If you get something like this that says that there is no total indirect effect, but there's only a total effect, and it matches the direct effect, what's that?
It should be the other instead of NA.
Yeah, it's because there's only a direct effect, and they'll actually match these up here perfectly, right? NA is right here. It's not a mediation at all. That's just your relationship. It needs to be AP tote. Not NA, AP tote, and AP tote. And now we run this again. And as we scroll down here, we get our R squared, and this looks right. So you have a total indirect effect, you have a total effect, and then you have a direct effect down here. What is the total indirect effect? A to B to, yeah, I'm sorry, path A times path B, right? Path A times path B, correct. This value right here will be the sum of all of these. Now, right now we only have one, right? We just have DTS to NA to AP tote. But if we had a second mediator, we would have DTS to NA to AP tote and DTS to mediator 2 to AP tote, right? And then we would have the sum of those two as our total indirect. So we're going to have some specific indirects, and you can have a number of specific indirects, right? And sometimes you will have competing specific indirects, where you have a specific indirect from one variable that's positive and a specific indirect from another variable that's negative, and you wind up with a total indirect that is 0, right, or non-significant. Also, you can have a specific indirect that is negative and a specific direct, or just a direct, that is positive, and that will wind up being an effect of 0, right? And so sometimes you find no mediation, and that's because there is a direct effect that is 0 and a mediated effect that is, or a direct effect that's positive and an indirect effect that's negative, and those two wind up canceling each other out. And sometimes, from a theory standpoint, that can be really important, right? And there's a number of different ways to explain it, but the most common way is to say that the direct effect serves as what? For my ARM2 folks. It's a suppressor, right? It's a suppressor effect. Yeah. So anyway, these are your three kind of important values here: your specific indirect, your total indirect, your direct, and your total, or I guess that's 4 things. And each one of these, actually, if we scroll down for indirect or for these effects, we actually get an estimate, right? This is a standardized estimate, which can be thought of as what? What is roughly an R squared, right? Now, more importantly, is the fact that each one of these indirect effects is relying on this effect divided by its standard error, so it gives you this. And what is this? What kind of test is that? That is a value. What's the estimate divided by the standard error? It's a test. What kind of test? Don't be shy. There's only a few. It's not a chi-square test. It's a z-test. Yeah, absolutely. Those values are all z. In several recent studies, Dave McKinnon has shown that the multiplicative term of a times b is basically never normally distributed, right? Which means that we've been using z-tests like the Sobel test to calculate the statistical significance of an indirect effect for a long time, using a distribution that never actually matches reality. And he has suggested a new approach, the first of which came out in a program that he developed called ProdClin, which is the product of confidence limits of the indirect effect. You can still use ProdClin. He's got if you Google ProdClin, PRODCLIN, you'll find a way to input your mean effect, the average effect, your standard errors, and your the bias within your model. And the bias within your model is found right here. It's called the scaling correction factor. And you can add in the scaling correction factor for both the H1 and the H0 model. And this program that he's built will correct your distribution based on those values. There's another way to do this. And what is the more kind of high-speed, low-drag? Any military people in here? No, just me. What's the high-speed, low-drag way to calculate indirect effects now? What's the sexy way? Yeah, it's to use bootstrapping, right? Who knows how to do bootstrapping?
We do it process directly, like we just.
Oh yeah, process does it.
Samples, they just take those 3 samples from the FSC.
That's exactly right, and that's exactly what bootstrapping is doing, right? It's drawing samples from your data, taking small chunks of data, running the analysis, and calculating a series of potential indirect effects based on the data that you've got, right? And then building a distribution of those indirect effects based on the data, and then using that distribution to determine your test. Really, it's not a test. It's determining the confidence bands around that distribution, right? So nobody raised their hand saying that they know how to do it, but everybody's going to raise their hand in about 10 minutes. All right. Yeah, shoot.
Backtrack, sorry. So there's like 3 or 4. Wait, there's 4 dependent variables. You got like drink, NA, CD, TS, and CALS. Which one is the moderator? Wait, mediator?
Okay. Which one is the mediator here?
What is the model?
Let's look at this. Okay. So we have NA, and we have distress tolerance and affect lability on NA. Then we have alcohol problems, and we have drink, NA, distress tolerance, and affect lability on alcohol problems. The way that I've set this up, alcohol problems is the most distal outcome variable, right? So this is going to be, if you're making an SEM model, this one is furthest to the right. And everything is regressed on there, so we're controlling for all of these things on alcohol problems. Then we're also regressing these two on NA, which puts NA right in the middle. And if you look at M+'s thing, right, here's NA. So NA is the mediator, right? And drink is just a covariate. Like I'm just controlling for the level of alcohol use for their alcohol-related consequences. And that's because what I'm usually interested in, and we can remove drinks from the equation completely if you want. I'm totally cool with that. What I'm usually interested in is what predicts your level of alcohol problems above and beyond the amount that you drink. And so that's what the model would look like without alcohol problems, right? Or I mean without alcohol use. I should have been more clear on what I was doing. I'm sorry. That's my fault. All right. So if we remove drink, we then wind up with a fully saturated model. And actually, let's remove drink because now we can see that affect lability is not predictive of alcohol-related problems. So let's drop drink so that our model looks like this. And before we do bootstrapping, let's do one other thing. Let's add in our interaction. And we're going to start by adding it in everywhere. That will keep this model just identified, fully saturated. Are you ready? We run this. Now we have our interaction in there. Now before, our interaction significantly predicted negative affect, right? And it still significantly predicts negative affect. Now we can see here that neither distress tolerance, neither affect lability nor the interaction between affect lability and distress tolerance predicts alcohol problems. Hey, how's it going? This is. For grad students? Come back in a half hour. In this instance, right here, I would say that there was no theoretical rationale to include this interaction or to include affect lability in the prediction of alcohol problems. And in fact, I might make the case that negative affect is fully mediating all of these, in which case I would remove all of those from that equation. And I would run this model like this. That's what the model would look like. You have alcohol problems and negative affect mediating all of the association between distress tolerance and emotional instability, predicting alcohol problems. A nice, clean, simple little model. Let's see what our fit statistics would suggest. Fit statistics are not terrible. That's not great. Could be better. RMSEA, this thing here is what really bugs me. That's 0.11 in my book, right? We're crossing that threshold of 0.10 that I told you I don't want you to cross. And I can tell you right now, this actually is not terrible, but I said I prefer this to be closer to 0.03, right? So we're just not quite at a spot that I'm comfortable with. And what happens is when we look at our modification indices all the way at the bottom here, it's going to say like, hey, here's some things that will make your model a lot better. I normally avoid these types of things, the with statements, but this right here, so it makes no sense to have alcohol problems regressed onto negative affect, and then also to regress negative affect onto alcohol problems. So I'm going to say no there. I can see right here that distress tolerance is a strong predictor of alcohol problems, and it will reduce our chi-square by 17.363. Whenever I add something like this, if my modification indices suggest that something is missing in my model, I might go back and say modification indices suggested that distress tolerance was a strong or robust predictor of alcohol-related problems, and then provide a theoretical rationale. This is consistent with previous research that has linked higher distress tolerance to lower levels of alcohol-related consequences, irrespective of drinking or something along those lines, right? And so we added that path and re-estimated our model.
What is that 17 value?
That is, it's M plus's best guess, because it's not actually going to be exactly 17.63, but it's M plus's best guess at the amount of chi-square that your model will lose, will go down, the amount that your chi-square value will go down if you add that single path. So that burns up 1 degree of freedom, right? If you add that one path, you're going to lose a single degree of freedom, but your chi-square will decrease by 17.343 or whatever it was. And a decrease of what value of chi-square given 1 degree of freedom is statistically significant. You can find this on a chi-square table, or you can recall from an hour and a half ago when I told you. Say that again? 3.84. Yep, that's right. 3.84. And so in that, among these modification indices, you can see that I put 3.84. That's because I'm saying, like, if the modification indice is above 3.84, that means that when I add that path, my chi-square will decrease by roughly 3.84, which is a statistically significant decrease, right, at a p-value of 0.05.
So if the MI was bigger than 3.84 and the relationship between the variables made sense, then I would
add it, yeah. And there are some people that will say that there are like these weird arbitrary cutoffs of 10 or 20 or 100. Personally, why have an arbitrary cutoff of 10 if 3.84 is a statistically significant level? Yeah.
So why are they recommending that you add in distress tolerance if it's already in your model?
I just added it to the model there. It wasn't regressed onto, it wasn't predicting alcohol problems. I just added it as a predictor of alcohol problems before you asked that question. It wasn't there before.
Gotcha.
So if we hit save, we hit run, we can now see, before, recall, there was just the single mediated effect from here to here. Now we've also added AP tote. What was our chi-square before? It was about 20, right? 20, and now it should be about 3. Assuming that that was right, and it is about 3. Degrees of freedom is 2. P-value for our chi-square, not significant. RMSEA looks fantastic. CFI TLI look great. SRMR is awesome. Everything looks good. We have a statistically significant interaction here still, right? And then we have our mediated effects. Now, in truth, you can report these mediated effects the way that they are right now. That's fine. There's nothing wrong with that. But my preference is to do something like this. We can come in here and say bootstrap equals, let's just do 1,000 to make things easy. And you cannot use MLR with bootstrap because you're bootstrapping. MLR stands, the R stands for what? Anybody know? It stands for robust standard errors, and it applies a correction to your standard errors. Bootstrapping is calculating your standard errors based on random draws, and so rather than using an equation to calculate standard errors, it's generating standard errors. And so you cannot use robust standard errors if you're going to use bootstrapping. Then we come down here, and we're going to put cint. If we just end it like that, it will give us confidence intervals for everything. Oh, who asked me about confidence intervals? And I said you can calculate them yourselves, Richie. You can just put in cint, and it will give you your confidence intervals. Yeah. I'm sorry. Then we're going to go BC boot. That stands for bias corrected bootstrapped confidence intervals. And we hit save, and we hit run, and if I didn't screw anything up, you briefly saw it there spinning, right? That was it running through 1,000 repetitions, 1,000 random draws, and our fit statistics will be just a little bit different because now it's using those random draws to calculate our standard errors, but they're pretty dang close, right? I think before this was like 3.1, now it's 3.7. All of this stuff is fairly close. The parameter estimates will be exactly the same. Standard errors will be a little bit different. You still get your standardized, and you still get R square, and you still get all of your indirect effects. And now, after all of that, you get all of the output again, but with confidence intervals. And so here's your estimate right in the middle. You have 0.5, 2.5, 5% confidence intervals. The standard is to report the 2.5, right? Because that is, anytime you do a two-tailed test, and you have a p-value of 0.05, that two-tailed test is actually looking at both sides of the distribution, right? And so it's 2.5 on either side. And so there are estimates. These estimates here will match everything up here as far as estimates go. And if we scroll down, we get our indirect effects. And this is our estimate of our indirect effects and our confidence intervals of our indirect effects. And then we have the standardized indirect effects and confidence intervals for our standardized indirect effects. And what that tells us is, when it comes to confidence intervals, we are looking at what? How do we know if our confidence interval or if our effect was statistically significant based on the confidence intervals? As long as they don't include 0, right? Yep. And none of them do. You can see here they're all negative. Those are effects, not confidence intervals. And down here, for applicability to asymptote, they're all positive, right?
Is it normal for the values to be like identical values?
To be what?
My values.
They are? That's not normal. No. Are your fit statistics the same as mine?
No.
3.722?
Can we see your input?
Yeah, let's go back and look at, is everybody's different from mine? Okay, this is what your input should look like. Just FYI, when you do bootstrapping, it's going to base the seed for the bootstrap off of the time of your clock. And so it will possibly have slightly different values just based on where the seed starts. It's probability, never going to be perfect. They'll be exactly the same if we use NLR, but if you use bootstrapping, it's possible that the random draws wind up being slightly different, right? But it shouldn't be major. It shouldn't be a huge difference. And if you were to up it from, I mean, obviously the difference will be larger the fewer bootstraps that you have, and it will be less the more bootstraps that you have. So if we up this to 10,000, it'd be very close. Whose input looks different from mine here? Anybody's? No? All right, so if we run this again, tell me if your fit statistics match my fit statistics.
Yeah.
They do now? Was there a problem with? What's that?
They don't match. Like mine says number of free parameters is 11.
Whoa, yeah, so that's not quite right.
Mine says that too.
Yours says 11 too. Okay, so look up here at UseVars. What do you have in UseVars? Does it look like that? What do you have in UseVars that's different?
How do
I had drinks though in there.
Oh, yeah, so I plucked drinks out,
I
right?
missed that piece.
Gotcha,
Oh,
yep.
mine thinks it's
Okay, so if we remove drinks, and now we rerun this, now, do your fit statistics match mine, or are they very close?
Yeah.
3.77. Colleen? Who does not have fit statistics that match mine? Anybody? Colleen, are we good? Good? All right, cool. So we've now run a mediation analysis, technically a moderated mediation analysis. We have found that we have a statistically significant interaction in between DTS and ALS predicting our mediator variable, NA. And then NA is a significant predictor of alcohol problems, as is the stress tolerance. What is our last step here? Okay, we've already done the figure. We have one other thing. So if we've done simple slopes, initially we've done simple slopes. We have one thing left, right?
Would you do like the conditional?
Yeah, right. That's exactly right. So right now, we have this model where affect lability predicts negative affect, predicts alcohol problems, right? But that first link from affect lability to negative affect varies. And so the indirect effects that we have right now are the indirect effects assuming that distress tolerance is held constant at its mean. But those indirect effects are going to be different if distress tolerance is high or if distress tolerance is low, right? Part of the cool thing about this is being able to say like, hey, if we can change distress tolerance, then we can change negative affect, and subsequently we can change a person's level of alcohol problems, right? So if we look at alcohol problems right now, from affect lability to alcohol problems, not using standardized, we see that it is 0.101. Let's go and change our distress tolerance. So let's see what happens if we can increase a person's distress tolerance by 1 standard deviation. We already know that that's going to affect that affect lability to negative affect slope. And what is the magnitude of effect on alcohol problems then? We are able to reduce it by roughly 0.04, and the ideal scenario is when we're able to actually eliminate the relationship between alcohol problems and emotional instability, right? So we didn't do that here. Our p-value is 0.022. Let's say just out of curiosity, and you can is that right? 1.76. That is 2 standard deviations, right? So let's assume that we could increase somebody's distress tolerance by 2 standard deviations. What would happen then? Well, let's have a look. It is no longer statistically significant, right? And even cooler, we can calculate regions of significance for the indirect effects, right? And since we're running out of time, we're not going to do it today, but if you calculate the regions of significance, you can pinpoint precisely at what level do we need to raise distress tolerance in order to eliminate the link between affect lability and alcohol problems. But we're not going to. What's regions of significance? We've done this in the past, right? Who knows what I'm talking about when I say regions of significance? Everybody who took ARM should have their hand up, or ARM 2. And then we have some people that are like, I can tell you like my absolute favorite graph, which I included in the video for this week, is a regions of significance graph. But regions of significance are when you are able to pinpoint the exact spot that something becomes statistically significant, or the exact spot that it doesn't, right? That the relationship becomes no different than 0. And I put a regions of significance graph and some instructions on web courses on today's module, so you can download that. So again, it's a thing that I made myself. Yeah, Richie, go ahead.
I just want to make sure I'm on the right track with looking at, I'm used to process, so like
Boo.
total and like total indirect, and specific indirect and direct.
Yes.
Go over those.
What they are?
Like, yeah.
Yeah, so actually it might be better if I draw it out, right? So, what's the tracing rule? Anybody know what the tracing rule is?
We didn't learn about mediation.
Okay. So, tracing rule says that 2 things. the indirect effect is the product of slopes, right, within that indirect effect, and the total effect is the sum of indirect, simple and total indirect effects, right? So if we have like x1, x2, and m1, and m2, and then y, and we have this relationship, and this relationship, and this relationship, and this relationship, and this one, and this one, we have a series of simple indirect effects, right? Let's call this A, let's call this B, let's call this B, let's call this C, D, E, and F. So we're going to have A to E, it's going to be simple 1, will be A times E, right? Simple 2 will be B times F. Simple 3 would be C times E. And simple 4 would be D times F. Does that make sense? And you're going to get some value for each one of these. Those are going to be your simple effects. If you add all of those up, those will be your total indirect effect. And it is really just adding. Like if this was like 0.04, and this was 0.1, and this was 0.5, and this was 0.05, your simple indirect effect would be 6.69, right? Then, let's say, for example, though, you also have this, and we will call this G. Then, for at least x1, you would have a total, you would have a direct effect of, let's say, minus 0.69. Let's say that this is minus, G equals minus 0.69, okay? Which would give you a total effect from x1 to y of what?
Sorry, say that one more.
Yeah, so if your indirect effect is minus 0.69, and but this is the total of your simple indirect effects. I'm sorry. We have to break that in half because only these two count for x1, right? These two count for x2. So what is our simple indirect effect for x1?
I can't really see 0.1.
0.14, yeah, 0.14. And if G is equal to minus 0.69, then we have we have two simple indirect effects, a total indirect effect.
I thought you said the total indirect effect is 0.6.
Yeah, I screwed up because I was adding x1 and x2. And you shouldn't, you can't, that's not the total indirect effect. The total indirect effect is only going to be from one variable. Yeah, my bad. So then if you have this is minus 0.69, you have a total indirect effect, which is just your two simple indirect effects of 0.14. You have a total effect of what? Minus 0.55, right? You just add those together. And so you get indirect effects by multiplying, and then you can just simply add those different slopes to give you your total effect. Does that make sense?
So the direct effect plus the total indirect effect is your total effect.
Yes. Direct effect plus total indirect. Yep, that's right. That's your total effect. And you can talk about it in any terms that you want. You can talk about it in your manuscript as these were the simple indirect effects, right? And then the total indirect effect was this, and then the direct effect was this. If there is a direct effect, maybe you say that there was no significant direct relationship between x and y, and consequently, for model parsimony or whatever, right? We removed that, and so there was no total direct effect, and consequently we have simple indirect effects and a total indirect effect, and no direct effects. It just depends on your model. Does that make sense? Yeah. Okay. Back to what we were doing here real quick. We can see that at 2 standard deviations, right, we have removed the relationship between affect lability and alcohol problems. And so you can go back and you can put together a table that has, here's the main effect, right? Here's the main indirect effect, total indirect effect, simple indirect effects, total indirect effects, total effects at mean levels of affect lability, or I mean distress tolerance. And you can actually do this in like 3 columns, right? Like here's low levels of distress tolerance, mean levels of distress tolerance, high levels of distress tolerance, and you could have a regression table that shows like all of these different effects at these various levels. Does that make sense? Colleen actually had the reason that I said that I like that table that you were making, she was showing me a paper that she's got, is because I think it's cool to get creative with some of these tables. Like,
It was Richie's idea.
oh really?
I'm
So-
Richie, by the way.
Yeah.
Credit me.
Yeah, so I mean, yeah, like subbing in moderators. I've been calling you Richie, haven't I?
No, I was
did I
just
just screw
making
that
sure
up?
that you give me the credit.
Oh, okay, gotcha. So no, I think it's cool though. Like, I love when people are more creative with their tables and especially with their figures, but also tables. So, and I wind up having to do that all the time because I want tables to convey as much possible information in a single table as I absolutely can. So, yeah. All right. That is moderation, mediation, conditional indirect effects using Bootstrap standard errors. Who knows how to do bootstrapping now? Oh, come on. You should all make it super easy. You just type bootstrap equals.
Quick question.
Yeah.
How soon do you post the videos?
Yeah, I'm going to go upstairs and post them right now.
Does it include audio?
Yeah, all of the audio will be there. Yeah, everything will be there. I'm going to redo the homework a little bit because the variables that I have right now up for homework are not centered. And so I don't want you guys to be struggling with trying to center stuff and then get it back into M+. If we hadn't lost a week, I might have been okay with that. But especially since I'm not teaching you how to move from SPSS over to M+, we're just not going to monkey with that right now. I will recenter the variables, and then I will put your homework up, and you guys will be good to go, and I'll get the videos up ASAP. Yeah.
Is the homework just due before lecture next week?
Yeah. So there will also be those of you who have had me before know exactly what I'm looking for, or roughly what I'm looking for in homework. Those of you who haven't, I will post a sample kind of homework assignment. The expectation is that your homework roughly follows a APA style results section, right? I don't get too hung up on, and I'd like you to throw in the last portion of a method section, which is your planned analysis. And so a brief discussion of planned analysis, what you're going to do with the hypotheses that I'm going to give you, and then move into the results section. I like to break up results section by descriptive and bivariate statistics, and I don't even care to see your descriptive and bivariate statistics, so I'm not too concerned about that. Though if you want to put them in there, you can. I'm really concerned, or more concerned with the main analysis or primary analysis, and in this case, the primary analysis is going to be a moderated mediation analysis. And I can tell you, like today we started with moderation and we worked our way through it. The best way to do this is actually to start with mediation and just include your moderator in there, and then say like the moderator was a significant predictor of the mediator variable. The indirect effects were this. Next we examined or probed the simple slopes of the moderator. They were this. Finally, we examined conditional indirect effects based on the moderator, and they were this. Like, I just feel like that flows better than saying like, oh, we did this model. First, we looked at the moderation effect on the mediator, which seems weird because you have to specify the whole model at once anyway. You might as well say like, here's what we found, and then do the moderation and then the indirect effects. But anyway, does that make sense to everybody? Yeah. All right, cool. That is it for today. I will see you guys next week.